The latest scientific breakthroughs are always revealing the links between Earth and Sun. For example, just recently the Schumann resonance was discovered to show anomalies directly above the epicenter of earthquakes up to 7 days before they happen. This might sound surprising if you don't keep up with these types of studies, but it's becoming common. Lightning itself is modulated by space weather, the sun's solar wind, and galactic cosmic rays. When you consider that sprite videos all appear to show the energy falling down through the atmosphere, the off-world explanation begins to make a lot of sense. And when it comes to the earthquake, and what besides the Schumann resonance might be sounding the earthquake alarm, you have to start looking at the sun. Scientists have discovered significant energetic changes in the atmosphere above earthquakes before they occur. Magnetic fields fluctuate. There are changes in the global electric circuit, including discharge events. We've also seen air glow, or earthquake lights, and documented positive ion emission prior to earthquakes. The only thing we know capable of affecting all of those is the sun. But how would that be possible? There has been decades of speculation about how the sun might trigger earthquakes, but the focus has been on sunspots, solar flares, geomagnetic activity, particle-based coronal mass ejections. We haven't really been looking at the interplanetary magnetic fields. We mainly see those magnetic fields stream away from the sun in coronal holes, but there are two coronal holes which are pretty much permanently fixed at the poles of our sun. Our focus today are those polar magnetic fields, and these can interact with the planets in a number of ways. They start at the sun and extend far, far out to the outer planets and beyond. Over the last half-century, scientists have shown that the polar magnetic field variation modulates sunspots, flaring, particle events, and other space weather indices that have been studied in the past, but each of those is generally deflected by Earth's magnetosphere, a magnetic shield protecting our planet. The interplanetary magnetic fields, however, can sync up and bypass our shield, dumping charged particles into our system. The solar wind undulates in waves of alternating magnetic character, and the Earth orbits the sun up and down through it, with the polar magnetic fields coming down and riding along the top and bottom. Lots of chances for interaction here, so we decided to test it. For those who have been here a while, you know that we've been expecting to be published in Earthquake Science by Springer. There was excitement on the part of the reviewers, our team, everyone, but recent events have caused me to decide to self-publish this study and ask that you all help. I'll explain at the end of the video. But for those who have been at our back, following closely, you deserve to know how we went from a recommendation for publication to making the decision to publish it ourselves. Here's the quick timeline and pertinent facts. On January 1st, 2014, I shared the hypothesis in our morning news that solar polar fields triggered large earthquakes. Over the next 7 months, I worked with Dr. Holloman from the Ohio State University Statistical Consulting Service to turn the hypothesis into a mathematical formula that we could apply to the data sets of polar fields and earthquakes. Let's go now into my account at the Earthquake Science Journal. We originally submitted the manuscript on December 2nd, 2014, and despite the holidays, we got a response on February 12th, 2015. Recommendation of publication after some editorial changes and a bit more requested discussion. Our revision window was closed a week early by mistake, but was reopened, and we submitted the manuscript revision on March 2nd. Then, more than 4 months went by. There were apologies for the snafu with closing the revision window too soon, and for the long time in reviewing the manuscript, the unreasonable delay. The journal was very kind and amenable. July 7th, 2015, another round of comments from reviewers, but this time we were highly enthused. Each commenter acknowledged the validity of the study and simply asked for terminology changes or more focus on the statistical results or more explanations, and we did exactly that. The deadline to submit was July 22nd, and as you can see on the right column, it says that a revision has been started, whereas below it says a revision has been submitted. The window is clearly closed, and it would appear that we missed our deadline, except that we didn't. Our manuscript was actually submitted on the 21st, a day early, and then, after our first window was closed and our second review took 4 months, something even more unusual happened. Here we see the latest messages from the journal to my co-authors and me. Let's begin with July 21st, confirmation that our second revision had been successfully submitted. Then, a few minutes later, they were kind enough to confirm by sending a second email, confirming that our submission was to receive full consideration and review. But later on July 22nd, we were asked to submit a PDF of our paper. When you upload a Word document to their system, it auto-generates an HTML file and PDF as well, and the PDF file was not so readable, so they asked me to submit one of my own. However, I never got the chance. Later on July 22nd, we received another email saying that our manuscript had been unsubmitted and was no longer going to be considered for review. No accepted or rejected, just out of consideration entirely. Since they don't have timestamps here on their website, let me go into my email for a moment so we can see when each message was sent. The July 21st message is obviously confirmation of our successful submission on time. Then we have the request for the PDF came in at 12:02 a.m., 2 minutes after the deadline ended, and then 138 minutes later at 2:20 a.m. our manuscript was removed and locked out, meaning that we cannot get in to change anything or submit the PDF they asked for. In the middle of the night, we were locked out in the span of just over 2 hours. We've sent emails to both Earthquake Science and their parent group, Springer. They have all gone unanswered. One phone call ended in a disconnection that I'll blame on the phone company for my own sanity. These are the magnetic fields of the sun. The purple and green are the interplanetary fields, and one must admit, this looks fairly complex, but due to the field variation and Earth's orbit through different heliospheric latitudes, the polar fields we measure actually have a nice oscillation between stronger northern fields and stronger southern fields, and then every 11 years or so the polar fields begin to reverse, triggering sunspot maximum, and you can see that the colors have now switched sides. This can be visualized graphically like this, the full data set of polar fields from Stanford University. You can see the 11-year pole reversal cycle centered around magnetic neutral, but also a shorter oscillation over about 1 year, responsible for those large up and down curves amidst the larger ones. This is largely the effect of Earth's orbit traversing different positions in the heliosphere. Now, we looked at both the north and south and the average polar field so we could determine if Earth was seeing more of the north or south at a given time and make quantitative analyses of those times as well. Dr. Holloman has said that the most striking aspect of this system is its simplicity. While the algorithm looks complex on paper, it is merely the mathematical language of looking for the peaks in magnetism and the polar reversals of these fields, where the magnetism is high versus where it is low. When does that one pole reverse? When is the Earth subjected to an average force reversal where the green line crosses the center? These simple factors are all that we used with the exception of a delay factor following big quakes, and we were only looking for those biggest ones. If the tectonic stress is triggered in a big quake, we shouldn't expect another one right away, so big events must be factors as well. Our results were convincing. Of the over 13,600 days surveyed, the extremes in magnetism and polar reversals cover about 41% of the time, but almost 79% of the magnitude 8 and higher earthquakes fall within that time. If there was no correlation, then we would have expected about 41% of the big quakes in that 41% of the days. We wouldn't have been too convinced with 50% or even 60%, but nearly 80% is a solid relationship of dependence, and there is a p-value of 0.00015. There's about a 1 in 90,000 chance of this result being random chance or error of that sort. So we feel comfortable suggesting that polar fields are a good candidate for exploring the Earth-Sun connection, especially in terms of earthquakes. What happened with our submission is done, and we cannot blame anyone or do anything but move on and hope that this manuscript will get the review it deserves to be either accepted or rejected by the scientific community. The manuscript is here for you to review if you are qualified, but if not, it is still a fun read, and this is where we'll need your help. There's a seismologist, geologist, geophysicist, or astrophysicist at a university near you. This information needs to get to them. This study is basic, it establishes the connection, but without yet being able to offer a predictive element for these massive disasters. Once there is dissemination, understanding, and further study of these processes, however, it may just be possible to use real-time solar data to predict earthquakes.